Yes. Yes. So why is that a misnomer, random variable?
Well, a variable varies. I'm not sure what you mean. We don't know how it. We don't know what a variable could be.
Sorry, Mayor. I'll probably get fired for saying, but that reminded me of that movie. What's it called? Strange Science or something. So what does a plumber do? No, sorry. Do you remember what the response?
I'm not quite sure what you mean by it's a misnomer. It's random in the sense of we don't know what it could possibly be.
Well, usually, when we talk about a variable, it's the argument, right, in a function. It's not the function, okay. Unless you have a function of functions. But anyhow, it's the variable is the x, right, the f of x. But it's an old term, and it completely is the wrong thing for modern terminology because they're functions. They're not variables; they're functions.
Okay, I see.
Right.
So whenever we say that this is a random variable, we're talking about the function that describes.
A random variable is a function on the sample space. So if your sample space is tossing the two dice, right? What are these outcomes? Let's go over. Don't take notes because we did this a million times. But what are these outcomes? What are they when you roll two dice?
What the numbers could possibly be? 1, 1, 1, 2.
Yes.
You just make your table.
Yes. Yes. So we've done some. We've looked at the probability of certain events, right? Like, for instance, we looked at the probability of snake eyes, right? What's snake eyes? Something like that. What was that, just to review?
1 out of 36.
Right. Somehow the sound got reduced on AIM. Did something happen?
Well.
Oh, now it's good.
There's a storm going on. It's raining at my house. So that might have a little bit to do with it.
Yeah, okay. I saw it light up just for a second. I wonder if that was lightning or something. Okay, but 1 over 36, right. But when we did the more interesting things, like on the test about this, we were doing what, for instance? We were going to look at what? For each of these 36 outcomes, we were looking at what?
Like a sum or a product.
Right, so the sum, that's a function on the sample space, okay? This is the sample size. I should draw it over here. Bad teacher. So this is the sample space. So the function could be the sum, for instance, right? That could be a random variable. So x would be equal to the sum of the two dice, right? So let's describe that function just a little bit. So what's the probability that x, the probability that x equals, say, 3? If x is the sum, well, the way we handle that is we look at when does this function take on the value of 3? Let's take a look. Only there, right? So the probability of the random variable is 3 is what? Are we good for this? So a lot of times we don't care about so much the particular thing that happened, but we don't want to know some function of it. Okay, but that's where we're sort of at here.
Okay. Yeah. Good so far.
Good so far. Now I don't know where to go except for that stupid movie. Do you remember what happened in the movie?
No.
We're trying to justify the boyfriend. The husband was angry that his daughter was dating a plumber, and she tried to make it sound like more than it was, I guess. She said, well, what do plumbers do? They plumb. I don't know. It's just ridiculous. It was a ridiculous situation, and you can't have a movie like that nowadays because of political correctness. I mean, plumbers make more than me, so you can't insult them. Okay, I wouldn't want to insult them anyhow. I've known some plumbers. Okay, so now I've forgotten what I was supposed to do. We did something else. we got this magic number E we were talking about. I remember we were talking about E. And it's kind of cool that what this is. And let's do a really simple example here. So you roll one die, and we want to calculate the magic number E. Now, E, it's not. It's different than probability, sort of. It's what you would expect to get. So X, you roll one die, and X is the result. Okay, result being what is it showing? Okay, is it a snake eye, or is is it a 3 or a boxcars or something? Boxcar. So E is called the expectation, and it's what we would expect to get out of this. If what you expect to get, the way you describe this is if the experiment was repeated over and over again, on the average, what would be the result? Okay, so you're going to look for, you want to calculate E, but this is really on the average. What do we expect to get out of X? Remember, X is, so what are the results that X could be? Let's go over it in our heads, right? It could be a snake eye, a 2, a 3, 4, a 5, or a 6. So we want to know that if it was repeated over and over again, what would be the average number? Now, this is something we probably can do without further ado. We just do it. But the problem is, I want you to understand that there's a difference between calculating probabilities and expectations. They're so different that I've approached statisticians and said, what's the relationship? There isn't any. They're different. And so I'm trying to explain to you how this difference comes about. But let's first see what needs to be done here. Well, by definition, this will be the sum over all X of i's, which are the values of X, times the probability that X equals X of I. I mean, this is the definition. And that's why I use a little triangle there. Whatever's happening that's different, there's definitely probability involved, but you have to understand that this is kind of a weighted average. It's like a mean, some sort of a mean. And that's different than saying, what's the 50-50 line? For like 50% of the time we get this kind of result, or something like that. That's a different question. And the word expect is very loaded. Okay, at the end of today, I want you to understand that it's a very loaded term. It really does convey the English what this is about. But let's just calculate one, and then we'll step back and see what the difference is. Probably. So how would we calculate this? What do you think we would do here? Well,
X of I is just a value that it could possibly have.
These are the different values it can have, right? And notice how it's important to sort of somehow indicate that there's a most accountable number of values. Okay, the math gets weird when you
because it's discrete. Like what we're talking about right now is discrete.
But as soon as you later on in the book, when they drop these conditions, you get into crazy things. Okay, but so what are the different values? These very good. That could happen. We can have 1, 2. These are the values of X. X is what you see when you roll, right? So it would be what? The first thing would be 1 times what's the probability of rolling a 1 with one die?
1/6.
Right, and we get a 2, and a 3, plus a 6 times 1/6. Now I don't know about you guys, but I want to factor out that 1/6, and now everything else is what? 1 plus 2 plus 6. And what's that formula for the first integers, the first n integers? What is it? It's 1/6 times n plus 1, right? Over what? Did I do that too quickly, or? Do you remember that formula for the first?
I do, but I'm a math major. I don't know about everybody else.
Well, let's just first get the answer here. What is the answer? Obviously, 7/2. But let me just review that formula, because this formula oddly comes up repeatedly in the book and the examples. Let's make a sidebar here. So suppose you have 1 plus 2 plus 3 plus 4. And what does this look like here? So if I hate to mention bowling, but this is a bowling situation, right? So with bowling, they set them up this way. And I asked people, what does this equal here? And somebody said, I don't know. Let me calculate it. Let me grab a calculator on the GE math. And I said, come on, man. If you get a strike, how many pins did you knock down? They say, I don't know. Well, that's it, man. It's 10, right? So there's a symbol. This is a sum of the first 4 integers, and it's 10. In general, S sub n will be n times n plus 1 over 2, and that's what I'm using down here. Okay, so we're whatever. That's the formula. I'm not. Believe me, I'm not going to prove anything. That's not going to prove it here. But at least it works out for bowling, right? If anybody wants to embarrass themselves and say they watch bowling on TV, professional bowling. I've done it myself. That's why I was making that face. All right. Okay. Now I want to try to give you some understanding of the difference between mean and probability. So the mean, the average here. So let me erase this. And suppose that you're in a neighborhood where there's home prices. I put them in. So if you have a house that's 200M, I mean, for real estate people, and this is a problem with teaching GE, it drives me crazy. And I asked the students, I said, well, houses, it's in the paper, the hot property section, house is 200M, for instance. And I say, how much is that in dollars? You know what they tell me, right? Try it, guys. Some of you guys are
200 million?
Yep. I don't know. The last thing they always say million. I'm saying, I don't know, That's pretty expensive. And they say, well, M is for million, right? Well, it's anyhow. This is a simple example. Suppose I have just these numbers. And 6. So probability is more like when you have these numbers, it's probability wise, it's like sort of where's the center in terms of where's like the middle of this. If you're looking for the 50% line, so the middle would be the median. Okay, and the mean is when you add everything up and divide by the number, right? Okay, so if you add everything up and divide by the number, what do you get? 8, 13, 19 by 5. That's approximately what, 4? So if the numbers are like this, the mean and the median, they're close to each other, okay? But I'm telling you, there's cases where the problem with taking the mean is that it follows the outlier. So if you're in a mean situation and you put E6 here instead of 6, you still got the same median, but what happens to your mean?
Sorry, what are you saying? E is just another number?
Oh, no, E6 is calculator speak for a million.
Oh, I see.
1 times 10 to the 6. So E6 is a million. I'm sorry. I'm going. So this is a million. A cool million. So now I want to know, not the median stays the same, but I want to get the mean of this. What's going to happen?
The weight is going to drag everything over to the right.
Exactly, by a lot. So it's heavily influenced by that. So what I'm trying to get at is the expectation, though it's much better for computation. You don't do inference for the median. You do inference for the mean, okay, if you're a stat person. It's biased towards extreme values, okay? So it doesn't substitute for computing probabilities. I guess for those that have had some statistics, you know what a distribution is. Okay. If you have a distribution with a very long tail to the right, the median is the 50-50 line where you've got 50% of the observations occurring. So where would that be? Now I have to be smart here. I'm thinking maybe like this. This is what I get for not being smart. I'm thinking maybe it's more like that. So this is the median. And what qualifies it to mean? Well, 50% of your observations are over here, and 50% of your observations are over here. Okay? So in a problem where they're asking you for what number, where you have probably 50%, that half the observations are below 50% or below, you return this like median number here. It's a probability. The probability for what this is your x. These are your x values, and if the probability that little x is less than or equal to that this median value, that's 50%. Okay, that's one type of thing. But if you start asking about the mean, that's a different concept. Why? What's the mean going to be? Where's the mean going? The mean will follow this because it's a weighted average. These observations way over here have a disproportionate effect on little e, this e here. So the mean could be over here. This is what you use for the mean, or you want e. So I'm trying to say that there's really different things. It's different statements. Probability statements are different than expected value statements. Okay, having said this, I have to show you the power of E. Okay, we're not talking about electric vehicles here. We're talking about, you can do some amazing things with this. Okay, so we computed one expectation. I'd like to compute a more realistic one. Last time we did another expectation too, right? The expected lifetime of a restaurant, right? That was one thing, but this is actually more profound. What I'm going to show you. I'm giving you the power of E, so you'll know why there's so much attention to it. Okay, let's take a look at this problem. Very similar to what we had before. So 4 balls are going to be distributed into 4 bins. Okay. Now, we've had a million of these problems already, but now comes some sort of the grown-up versions of them. A question could be asked, what is the expected number of empty bins? And I know I'm in the way, I'm sorry. So let's go over the question, make sure we're in the right ballpark here. What is the situation? We have 4 balls. They're being randomly thrown into 4 bins. Sometimes when I teach the course, I have to keep repeating, every throw goes into a bin. None of them miss and then go someplace else. I think that's obvious, isn't it? But anyhow, it's in the past I've been bedeviled by that comment multiple times. So they're going randomly. It's a little bit similar to what we did before, right? 4 balls into 4 bins. But before, we had probability, right? We had probability questions, like what's the probability that we have 1 empty bin or something like that? I kid you not. What I'm giving you now is the world's best example for this. It's the world, and it's not my doing. I downloaded a book on probability for computer science, and this was the first example they gave in the entire book. Okay, so if you're using this formula, tell me then, so what we've learned today, if we've learned anything. If we're using the formula, how could we calculate this? So we have to define x. X is what? X would be equal to this random variable. The experiment is to throw all 4 balls, right? And to see how many empty bins, if any, you have. So this is the number of empty bins at the end. Okay? So if we're going to do it with this definition of the expectation, help me out here. what will we need to write?
Well, we need to first off list the possible values X could be, and then find the probability of each one.
Very good, very good. Does everybody hear that? I mean, you're ahead of the game, but I want to make sure everybody gets that. We have to apply this definition. It's saying these are the different values of the random. What is a random variable again? At the end after the outcome, we've done the experiment. You throw in the 4 balls. The random variable counts that it returns the number of empty bins that remain. Okay, so so it could be what? It could be 0 empty bins times what? X equals 0 plus 1. Well, this is a wonderful thing. This is a nice thing to calculate.
I was going to say I need to figure out what that probability is, but we could just label it as such.
Right. This is what we like to see when we're doing these problems. Okay.
Yes.
You don't want to see this after you spend a lot of time taking my test and computing this, right? Then it's 1 times the probability that X equals 1, and I'm running out of space, which is the story of my life, and so I have to erase what X is. But I think you understand what it is. Plus 2 times the probability that X equals 2, plus 3 times the probability that X equals 3. Now, do I have to worry about 4? Could I have 4 empty bins?
You can write it down, but the probability is 0.
Yeah, you can't have it. So let me ask you this general question, okay? There's no expectation now. We evaluate, we know what to do. This is a probability question, right? It's a probability question. I can answer what they want if I just calculate how many probabilities. How many do I have to do? 3. How hard is it to do those? And I say this honestly, not like I know how to do it and you don't. Not like that. No, it's not easy. Every time I try to do them, sometimes I make mistakes. These are not that easy. I mean, I think we had actually done some of these on a test. If you remember what they were, it would help. I wasn't going to do it, but you know what? In order to demonstrate this, maybe I need to do some stumbling here. Which one do you think we should try? I mean, you think this one is reasonable? Probably the next. They all go into the same bin. So what would that be? What would that be? Okay, we've got an honest professor, you guys.
Okay, well, hold on. I haven't done any of them yet. I'm trying to think about it. The first thing that I want to do is count the number of ways that you could possibly put the balls in the bins, period, just to get like the denominator.
The denominator.
Brandon asks, why not 4? Brandon just asked the question of why is it not possible that X can't be 4?
Oh, I'm not sure. I think he's asking about this. Okay. Are you sure, Brandon? I'm not sure what he would be asking. Let me check. Why not 4? You can't. Okay, you've got 4 balls, right? And they're going into those bins one way or another. So they got to go somewhere. So you can't finish the experiment with 4 empty bins. You can get 4 balls in one bin, so 3 would be the most empty bins you could get. Is that good? I thought you were looking over here and say, why not evaluate that? Well, because it's multiplied by 0. Okay, so let's get back to Ames' question of how are we going to encode the results of this experiment. And again, I was not planning to go down this path, but honesty has gotten the better of me here. So let's do it by, as we did the test, right, or those problems like that. Let's do it in vector notation. So,
Professor,
yeah.
I'm sorry. So I was doing something. I came a little bit late, so I don't know what's the setup to this experiment.
It's pretty easy to explain. You've got 4 balls and 4 bins, and we're tossing those 4 balls into the bins randomly. We've had this situation, I think, this scenario before, and what we want to know is the expected number of empty bins when we finish this experiment. Now, expected number just means on the average, you perform this experiment over and over again, how many empty bins would you expect to get? So to make it concrete, we want to calculate E for that situation. So E of X is the number of empty bins, and the definition of E, or expectation, is the different values that X could have and multiplied or weighted by their respective probabilities. So we have to evaluate this somehow. And here we have it down here. So all that's left is to figure out these probabilities. It's not you don't have to worry about the E anymore. You just got to get those probabilities. And I'm not sure I can do it on the spot right now.
Wait. What's the brackets with X? What does that mean?
Oh, this is the expectation of X. So this is sort of some type of average value X achieves. But it's a huge concept in statistics because probabilities are hard to compute. They just can be very. And we're going to try to do it right now. I'll probably fail. However, expectations are much more amenable to computation.
Okay, I see. And so we're trying to find the
these probabilities.
The expectation. Why is it the sum of? Why is it equal to that equation?
Oh, this definition.
Yeah.
This is a definition. Oh. So expectation of random variable X is the sum of all the products of the different values of it can take on times the probability that it takes on those values. But Ethan, let me just focus on let's try to pick up where we were, because all you're going to do is do these probabilities, which I think we've already done on a test or mentioned in class or something.
And so X just means the number of empty bins here. Right?
Yes.
Okay.
So I'm going to encode what Aim was asking. How do we get the denominator in here? So I'm going to encode the result of the experiment as this vector with this 4 tuple. What does this 4 tuple mean right here? The first ball went into 2. The second ball went into 3. Third into 3, and the fourth into 3. How many empty bins do we have here? If that was the
2.
2, right? But Aim says, well, how many different equally likely outcomes are there? Well, the first ball can be what?
It can go into any of the 4 bins.
So what is it?
So 4 to the 4th.
Very good. Otherwise known as, if you're a computer person, you know all those powers of 2. So let me throw you for a loop. What's 2 to the 16? It's my favorite number.
Oh, wait a minute.
No, yeah, okay. You know it, right? How would you know? How could you remember it? 2 to the 16.
It's actually, I'm still trying to. I'm having brain freeze right now on that one.
Okay, let's just keep it in the back of your head. And let's make progress. Try to make some progress. Let's see. This one should be easy. I don't know that I'm capable of doing these right now, but what about this one? How many outcomes have it that all of the balls go into
It's the fun.
So what if you have 2, 2, 2, 2? How many outcomes are possible, Aim? This is what? There's 4, right?
Yeah.
So
it could be all 1s, all 2s, all 3s, or all 4.
Yes, I really need another color, which I don't have. That's getting good. I'll put up 4 there. Now the things get tough. This is going to be hard calculating. What's the probability that we get 2? How many ways can we get 2 empty bins? This is not good. What does it mean to have 2 empty bins? Well, maybe you got 3 here and 1 here. Oh no. How are we going to calculate this?
Well, first you have to choose which 2 bins everything's going into.
Okay, I can do that 6 ways, right?
Right.
So I'm going to have basically 2s and 3s, right? Like fingers and toes?
Right. Then you have 2 options for the first ball, 2 options for the second. So 2 to the 4th.
You remembered how to do it. You remembered. You remembered how to do it. And we have to eliminate some cases here, right?
Right. Then we have to limit the case where it's 1 in each. So, there's 2 cases of that.
So we just dodged a bullet. So I know there's a problem somewhere here, but we dodged a bullet. So what's that number? What is this? 16 minus 14 times what? Times 6? Do we do this right? So this is 16 minus 2 is 14 times 6?
Yeah, I think that's right.
Aim's being quiet, so I don't know. Maybe.
Yeah, you're good. You're good. I'm a math major, not an arithmetic major. I'm really slow with that kind of thing.
No, don't say it that way. It doesn't give respect to her. You should say, not an arithmetic major.
Okay.
we gotta sell whatever we have, right? You know,
Sure.
plumber's plum, right? I mean, that's what they do.
Okay.
Okay. What about this one over here?
84. Okay, then we're gonna kind of use the same idea. We're going
Oh,
to
I don't know.
choose-
This might be the end of me today. I don't know.
Okay, well, we don't need to use the same idea. We could use something else.
I don't know. So what does this mean? This means that there's one number that is missing, right? So how many ways could that occur? Well, there's 4 ways we could choose the missing guy, right? Like missing in action, right? Chuck Norris or something. So like there's no ones, right? So I have 2s, 3s, but I can't do that because that would mean 2 numbers are missing, right?
Right.
So this is just an awful thing. So we really have to think. Could some number show up? Could a number show up 3 times in this, and then still have only 1 missing?
I don't think so.
I don't
So I
think
think
so
we
because
have. I think this is the case where it has to be one number. It has to basically be the pigeonhole situation where it's like
well,
one
you
for
can
each, except one of them has 2.
yeah. Yes, I think we're going to have one number appearing twice, right?
Yeah, exactly. One number.
So
appearing twice, I think.
that's of the ones remaining, right? So how many numbers were remaining here? We already took out 1. There's no ones, but the ones that remain, we have to decide who is going to be the one that is doubled, right? If you look here, 3 got doubled, right? And there's 3 ways to choose a number that's doubled. But then what about location in here? Location matters, right? So
Yeah, huh.
4 choose 2. Stop me if I make. I'm sorry, you guys. This is just they don't pay me enough to get this right now. So the location of the 3s matter, right? Not just who gets doubled, but where they are. And then we know that the other 2 guys are still there. Now it's pretty complicated. There's a 2. We know there's 2 single numbers, but they could be. It seems to me there's 2 different ways it could show. You could have a 4, 3, 3, 2, or you could have a 2, 3, 3, 4. You guys, are you roughly comfortable with this, or?
It's not the way I would do it, but that's fine. The way I would do it is I would look at, I would calculate probably if x equals 0 and then just do 1 minus everything else. Or excuse me, 4 to the 4th minus everything else.
Okay.
So I wouldn't even have to look at the probability of x equals 1.
You were going to look at.
Okay, so the probability that every single bin is filled, I think that one's pretty easy. Because it really is just a number of orderings of 1, 2, 3, 4.
So you're going to go. Okay, that's sorry, I'm slow here.
I'm doing something completely else. If that's really what it is.
I get it, but you're going to do a complement. So
yeah, exactly.
So you have 1 empty bin. The complement would be you have
not 0, not 2, not 3.
2 or 3. Mm-hmm. Right. I don't know. Did you get a number for that? See if you get the same number as this. I don't know.
Sure. Yeah, I'll do that.
Let me just.
So you're taking the final 3 terms and just putting that all as the complement of the first term?
Yeah, but there's also a term that you see, I didn't want to calculate.
We don't need to because it's 0 times. That's true. I see that. But I think that finding the probability of x equals 0 is easy.
Let me just.
I think I see what you're doing. I think I know what you're doing.
There's no guarantee in life, but you know what? I'm going to put down my number. I'm going to make the gamble. So this is what? This is 24 times 6, is it not? 24 times 6, which supposedly is 144. So I don't know if this is what Anne gets when she does it, but I'm getting 144 here. And I think I need to grab the calculator. I probably should double check my reasoning on this.
Yep, I got the exact same thing. I also got 144.
Wow. Well,
yeah.
Then it comes down to this, whether this was correct. But you guys were watching me when I.
Oh, it better be. Because I did that. That was this. I did the same thing.
Okay. Good.
So the 212 total.
The 212.
Wait, so
Oh,
4 to the 4th is 256.
This is 144 plus 168, right? But I didn't multiply the 2 yet.
Oh, well, yeah,
Oh.
well, whatever. I was just making sure that the numbers made sense. But yeah, 144 plus
So what do you get to the
times
total?
Where are you getting the numbers to get you the
These numbers?
144? No, the 144 and 84. Like, where did you get the numbers from?
We determined it. I mean, I was calculating it.
But yes, but those numbers, where did those numbers come from? The numbers you determined it with.
Oh, these, like this one, what was?
Right, so where did those come from?
Oh, well, then you have to, okay, I think, I'm trying to remember which one this applies to. I think it's.
That one's the 144.
It's the 144, okay.
Yeah.
So this has one empty bin, right?
Mm-hmm.
So the 4 is the choice of which bin is empty. You got 4 choices, right?
Mhm.
Then we determined that another number, one number, has to appear twice, exactly twice. It can't be more than twice. And so there's 3 ways for the 3 choices of that, the additional number, besides the one that didn't show before. One of the ones that does show has to show twice, so we make that. But then the 4 choose 2 are the locations in the vector where that repeating number shows. And then the other 2 numbers that must show, there's 2 ways of laying those down. So when you're looking at these 4 tuples, this is how many cases you have where there's exactly one empty bin. But I still haven't calculated this down here. Does anybody want to do this on a calculator?
I've already done it.
What is it?
324.
But,
And then if you actually do that division, it's 1.265.
hang on. You're good, but can you give it to me as a reduced fraction?
As a reduced fraction. Oh, well, hold on.
Because that's how I remember it. I don't remember it as a decimal. So if you have a-
81 over 4 cubed, which is 64.
I think I remember that as being correct. So
Yeah.
okay. So I'm sorry, I kind of rushed this. Maybe I don't know who I was talking to. Maybe I could.
Yeah, I asked that. The
Could
2
I-
still does not make sense.
This last 2.
Yeah.
Okay, let me give you a concrete example of this, okay? So the 2, so you've got one number that what does not show, so there'll be no 1s, right?
Mhm.
And here's your 4 tuple. You got no 1s, and then some number is going to show twice, and then you have to figure out where it's going to show. So maybe it shows.
Oh,
right?
I see.
Now you have to have a 3 and a 4. Otherwise, if it's 2 3s, you're out of luck. Okay, so there's 2 choices. So you can have a 3 here and a 4 here, or you can go vice versa.
So that deals with whichever bin is going to get more than 1?
This deals with the bins. Yes, this deals with the repeating one.
Mhm.
This deals with the 2 single guys. There's 2 bins left at that point, and the 2 guys, the 2 numbers you have left that must both show, they can be put in one way or the other way, vice versa.
So the 4 choose 2 shows which bin has more than 1.
Yes, which bins, right? I have the
Right.
Yeah.
And then the singular 2 is pretty much deciding the remaining 2 which way they go.
Right. I hope I did
Kind of
it
like a
right.
coin flip sort of thing.
Okay, how did I do this? The 2 is a repeater, right? But your 3 and 4, right? Here's your coin flip: 3 and 4, or 4 and 3. There's no 1s.
And the 4 is the total number of bins, and the 3 is the number of bins with balls inside them.
Yes.
Okay.
I think so. So the 3 is the 3 is the choice of the repeater, right? So there's 3. It could be, you could have 2 2s, 2 3s, or 2 4s. So that would be the bin, right? That has the multiple. Okay, guys. Let's.
I realized that so there were a lot of threes and a lot of 4, a lot of 3s, a lot of 4s, a lot of 2s, and all of that. Our end result is 3 to the 4th divided by, or no, 4 to the, wait, it's 3 to the 4th divided by 4 to the 3rd.
Interesting.
I just thought that was kind of funny.
Well, there could be something in that. So look, I got to close this story here. So this is chapter 1 in a book for professors and graduate students. First example. Why is this example? Well, he says, go ahead, evaluate it. He says, you can do this in 5 seconds if you use the properties of expectation. So let's just keep this thing down here, but let me erase this. Let's approach this pretending that we're physicists. What do physics guys like to do? When they do a problem, they look for what in the problem?
Symmetry.
Very good. It's the first time I've asked that question and somebody got it. Okay.
I have
that's the first time it's happened. That's the first time it has happened. Okay, so I got a new one. Yeah, I'm glad I didn't retire already or die already.
Yeah, I actually have an associate's degree in physics. That's probably why I knew that.
Okay, so can anybody suggest, is there some hidden symmetry in this problem? I mean, what's happening again? Let's go over it. You have these 4 balls being thrown into the 4 bins. From the point of view of what, does it look exactly the same? Imagine you were one of these bins, okay? Here you are. Here I am. I'm a bin, I'm a has-been. No, a bin. I'm currently a bin. And what do I see? I see these balls getting thrown. And what's my chance of getting hit in each one? The ball is equally likely to go in any bin. So my chance of getting hit on any throw is what?
On any throw is 1/4.
It's a quarter, but notice it doesn't matter if I bin 1, bin 2, bin 3, or bin 4. It's the same situation. Now, where in this does it exploit that? It doesn't. So let me show you. This is the technique, okay? And I realize this is bad teaching because I'm giving you the slick way to do something when they want you to slog through this way. But this is why people get into this field and they like it, because it turns out there's sometimes you can really get to the heart of the matter very quickly. What property of the expectation do I want to exploit? Well, if I had 2 random variables like this, what do you think would be the best of all worlds? You have 2 random variables, okay? Like this, two different, 2 different functions on the sample space. So we're looking at now the things that get generated. Like there's a global function that's x plus y, so g or something. So the expectation of that, but what would be the easiest thing that this could be? Those that took calculus probably are linear.
Really hoping that this is expected value of x plus expected value of y.
Absolutely. This is called, it's an example of the linearity of the expectation, okay? The linearity of the expectation. So now this is the only tricky part. What should our x and y and w and z, what random variables should we pick here? If you get this, it'll be an aha moment, and you'll be able to drive home. You're able to spend the rest of the day, with some feeling of accomplishment. We need to take this problem and realize, you know what? I shouldn't have been working with this x down here. It's the wrong way to approach this. What we should have done is this. So we should have said that xi equals, it's 2 things. It could be 1, at the end of the game, after the experiment is run, if bin I is empty, it's running on empty, or 0 if bin I is occupied, OCC. And you can't read the Y here, sorry. Maybe I could bold it in. Will that overcome the glare? This random variable is a strange random variable, okay, to somebody who's never seen it before. If you've never seen it before, you're about to be educated in probably the most powerful technique in the entire book. They call it an indicator random variable. Indicate, like a light, a warning light indicates whether it's on or you got a problem. If it's off, you're okay, right? So indicate, it's 2 states. It's 0, it's yes, no, true, false, on, off, 0, 1, like that. I think there's another name. In our book, they have another name for it, but they're really known as indicator random variables in computer science. Very simple random variable. So again, it's the opposite of what you would think. It's going to show 1. It's going to return 1 on your sample space if bin I remain empty after those 4 throws, okay? And it will be 0 if it got hit. And when I say hit, it could be hit by 1, 2, 3, or all 4 of the balls, right? But this is the function on the samples. The the sample space is the scenario outcome, right? What's in every bin, right? What's in your wallet? What's in every bin? So this function will return, and I is what? I ranges from what to what? How many bins we got here? We got 4 bins, right? OCC is occupied. So what is the trick? Now this is the big trick. What can we do to set this up so we can use that linearity of the expectation? What should we do? This is the only thing, this is the stretch, okay? This is the little stretch. What should we do with these? We want to count what? We really want to know what? How many empty bins we have, right? So how can we express the total number of empty bins in terms of these indicator random variables?
Thought, at least just to write it down, is get the expected value of x1 plus the expected value of x2, just expected value of x1 plus x2 plus x3 plus x4.
That's it. Have you done this before? I'm just curious.
No, this is the first time looking at something like this.
Okay, very good.
I was so proud of myself for getting the problem down there. I'm like, you want me to do it again, but differently? How dare you?
Yeah, but the point is...
Yeah, no, it's fine. It's fine.
The point is this guy is writing a book, and I still have it on my hard drive. I haven't read much of it, but he's got everything for computer science, the discrete kind of stuff. Okay, so let's take one more step than what AIM is doing. Let's not multiply. That's something else. Let's just write x is this. Now look at this carefully. This x is the same x we got down there. This, at the end of the experiment, this x will record how many empty bins there are, right? Because if like x2, if it was empty, that will return a 1. And if the others are occupied, they'll return a 0. So in that case, you have 1 empty bin. This random variable expressed this way is what you want. Okay, so now we'll do what AIM said. So she's saying to do what? She's saying you take the expectation of this side, it is the expectation of this side, but because the expectation is linear, what do you get?
Oh, that is really cool. So it ends up being one smaller computation, and you just multiply by 4?
That's it. Maybe you should get into the field. I made a mistake here. I meant that to be a 3. X4. Now, I was saying that so what is E of X1? It's going to be 1 if it's empty, right? So what's the formula for expectation? It'll be 0 times the probability that X1 is 0 times the probability that it
is not empty, that it's occupied, right?
Yeah, okay. I got it. I have to compute an expectation. Sorry. So E of X1. Okay, so what are the different values could be? It could be 0 times the probability that X1 is 0 plus 1 times the probability that X1 is 1, right? So it will be, the answer is the probability that X1 is 1. That means that it's empty, right? What's the probability that it's empty? Well, you got 4 shots, right?
The 4.
They're all independent. So what is it? The probability that this guy survives. So, okay, there's 4 of these, right? But this one here is 3/4, and they're independent. So every shot had to hit something besides X1, right? And that the probability of the hit, it's 3/4 for each iteration, and these are independent. So you have multiplied these. So it's to the 4th, right? That's for E of X1. But as Ethan said, the symmetrical situation for the other bins means we can do what? We can do what? It's the same thing for all of these. So what is it?
Times 3 to the 4th to the 4th. Excuse me, 4 times 3 over 4 to the 4th, which is the same thing as what we got earlier.
How do I know it? Because Ethan had done some sort of factoring or something.
I factored it. I was like, that's got a lot of 3s. So I was like, oh, it's 3 to the 4th.
And let's just to verify it. So 3 to the 4th is 81, right? And 4 cubed, I ought to know that. 16 times 4 is 64. Well, what do you know? Now, you might say that both were equally complicated, Di, because it took you the same amount of time to do both. No, I'm telling you, if I know what I'm going to do here, if I was just doing it on my own, I would just whip through this. I don't have to think, I just have to do one.
That's actually really cool. I don't know. It's like, I like how you use an indicator variable. To me, it's just like bit flags. And it just makes me think about, programming, because I'm a programming nerd.
Well, thanks.
So,
I thought it was
that's really cool how it's simplified.
But the idea, of course, is to use this technique with abandon. So you use this technique in hashing, in average case of algorithms. Okay, like I don't know if you heard of the quicksort algorithm. I don't know if you did that one, but there's an analysis of the average case of quicksort, and the average case is n log n. But anyhow, this is critical. This kind of thinking to get the answer. And I remember as a kid, my dad was a mathematician, and there happened to be around the house I think that notices of the AMS or something like that. It's just for general interest mathematics, but very well written. It was like in 1967. And I looked at it, and there was a probabilist, who did the average case analysis of quicksort, and it was just beautiful. I mean, I could sort of get the idea looking at it, what he was doing, and it's just like this, but a little more sophisticated, because with quicksort, as sorting routines, they're sequential. So somehow you've got to take the sequential aspect out of it, and get to what? What are we looking for? E, right? This would be the average number of comparisons. That's a measure of the complexity of the algorithm. It's actually in our book, beautifully written, like everything else in this book is, right? It's beautifully written, right? Maybe too beautiful. It's aesthetic, but then we can't understand what he's saying, because he wants to say it pretty rather than clearly.
Yeah, I can agree with that.
Okay, so let's if there's any question, a lot of guys went silent, but I do appreciate your attendance. I have, in my opinion, I have excellent attendance, considering that you guys are going to be on break for a week. So I'm very happy that you didn't get airline tickets for yesterday. In this way, I guess you could still take the class, right, on your iPhone, your cell phone. I guess you could, right?
It's kind of also a bad time to be flying anywhere. So, I mean, that might have a little bit to do with it.
But do you know how cheap airline tickets are right now? It's like you're gambling with your life. It's like, man, I'm thinking.
Well, yeah, I don't want to be gambling with my life right now.
Yeah, but it's like pretty darn cheap. And I did fly somewhere, and what killed me was when I made the reservation with American Airlines, I saw all these empty seats. I say they're going to separate people. Guess what they did? They maxed it out. They just maxed it out. And I asked the attendant, "What are you doing here?" And they said, "This is what we always do."
Jeez.
But anyhow, I never seen such cheap airline tickets. I mean, it's okay. Let's talk about another concept. Okay, so the variance. So we have E. E is sort of like the mean or the center in some sense. Is this the center of mass? I mean, I hope you guys you took calculus, right? So you guys know about center of mass. So center of mass. Suppose you have this. There's no weight here, but you have a big weight here. Okay, there's your 120-pound dumbbell. I used to be able to move those. Now I can't do anything. And here's a small weight right here. So the center of mass is what? Right in the middle? No. The center of mass would be a place where if this is a seesaw, it would balance. And you might say, there's no way that heavyweight, that heavyweight's going to win no matter what. Well, that's not the way it works. You guys, you remember the seesaw, right? Now, come on, man. You guys are way younger than me, and some big heavy kid sits down, pow, the other one goes in the air. You know how it works. But the little kid depending on where the center of this fulcrum is, this can actually balance this. This small guy is leveraging this guy, right, to a draw, right? So, so the mean of these waves, the location would be the center of mass. This is it. This is your E, sort of your E spot here, where that's whatever. The torques, what's happening are the two torques around that fulcrum. They're the same. And torque is what?
That's like a rotational force.
But it's distance, right? It's the distance times the force at the end, right? As I recall. Okay, so let's look at it in a couple cases. If you had a distribution, suppose that you have 100 here, some random variable has 100 over here. So it takes on two values. So in this case, E is what? How about minus 100? This is at minus 100 has 100, and this is at plus 100. Let me be smarter, okay? Just if you understand when I make this blob here, that's the same way. So whatever that is, when we're computing E, let's say it's 1, okay? So this is 1. So your random variable is giving you 1 and minus 100. And 1 at plus 100. So what is E for this? Well, E is what? It gives me 1 and minus 100 and plus 1 and 100. What is that equal to? So the expected value of that random variable is 0, okay? But what if it was a little different here? What if this was 1,000 minus 1,000 and 1,000, and we still got the same weights here? What's the difference in the situation? Well, you still get 0 for the E, but your two values that the random variable takes on are much more spread out. So it's not just what the center of mass is. The center of mass can be sort of deceptive. I mean, there's nothing here at the center of mass, that they say for a place of great importance, there's nothing there, but it carries a lot of weight, But so there needs to be more than just the expectation. You need something else, some measure of the spread. So if you have people that have studied statistics, what's the case if you have a normal distribution? Well, if it's a standard normal, it's sort of like a measure of the spread. It's the standard deviation of sigma. Now you might say, well, where is the sigma? Well, it's the place, the inflection point of that distribution, okay? When I say distribution, I hope I'm not confusing people. Imagine a histogram, an idealized histogram. Are you okay with Are you guys okay with histograms? I mean, I would be. This would be a ridiculous if I'm talking about. This would be ridiculous if I'm talking about variance without talking about histograms and distributions of that nature. I assume that you had some exposure to it in high school, but do you want me to give you this? Somebody said no exposure to concept of a distribution or histogram. Somebody said a histogram sounds like a medical test. No, that's not. No, it's my eye. Sorry, I read it wrong. Okay, do you guys understand what a histogram is? You're trying to get the distribution.
It'd be worth talking about.
Okay, good. Okay, well, I'm sorry. It's a story. With Dye, everything's a story, right? It's old people. That's all they do is they tell stories. They don't do anything anymore. So let me give you the histogram story. Why are histograms useful? Well, what you do is you collect data, and depending on what you get, you put them in little boxes. And when you have the same range, the data going in the same box repeatedly, you just make it a tower there. So it could be that you have various data, and you're going to grid you're going to make, they call these boxes or bins, buckets. Okay, buckets is much better. So to make a histogram, you need buckets, okay? And if your number lands here, then you make one brick over that. If a number lands here, you make a brick over this. They might say, what if it's a pole sitter? What if it lands right in between two, right? Okay, now if it's a continuous distribution, that can't happen. But you have to, if it's a discrete, you have to have some plan for when it's right in between. Either it's always go to the right or the left. So if I get another data value, that I've collected here, then I get another box like that, okay? Now this could go on, and you might end up with, sorry, my drawing skills are very, very rudimentary. You might end up with something like this, and what's happening here? Well, you once you get enough of it and you rescale it, because it might go through the ceiling if I don't rescale, then you can do something like this to try to determine what the underlying distribution is you're sampling from. Now, somebody's got a question here. Sorry. No, correct. No, why not? Floor, no, okay. Okay, so this is just data collection and how you're going to display it. And the idea is that when you display it like this, the data, you can see if the data are telling you a story, okay? So what was the story, if I would make a histogram of my first midterm that I gave you guys, what was the story I told you? What was the story? So if I made a histogram...
It's bimodal?
Yes, it looked something like this. And again, this was that center mass thing, which was carries a lot of weight, but there's nothing there. It's empty space. But anyhow, so I had scores in here, and I had scores over here. I won't put the numbers. I don't want to make a point of it. But this is telling a story, right? So there were lots of scores down here, and there were boxes, the bricks going up. There's lots. It wasn't exactly like that, and I guess this one was less because it was a hard test. You know what I mean? So the history, when you display your, does everybody understand what I'm doing here? So this would be like, I don't know, somebody who got 70 up to say 100, even though nobody got 100 or very few. So those scores, like maybe I'm going to have my bucket width of 10, okay? So 70, 80, 90, 100. So you fill in a brick every time a data value lands in there. Okay, so this is a story, you guys. It's a true story. You can look it up. How is it possible that somebody used a histogram to get a lot of money? Okay, Caltech. You know the story about Caltech. The people that go there have a history of thinking outside the box, no pun intended. And there was a guy who was a student there. I think he was a graduate student, and he decided that it would be nice to take he'd like to take a voyage in a yacht around the world. And of course, he didn't have any money to buy the yacht. Yachts back then, by the way, were expensive as they are now because they're all handmade, right? Okay, so it's not like a steel hull thing, it's something different. So anyhow, this is a true story. What do you think occurred to him? He wanted to make a histogram of something, okay? So let me ask you guys, you know what a roulette wheel is? A roulette wheel, it's got 38 equally spaced divisions there, and they throw a ball and it spins around and it randomly goes into one of the 38 spots. So if you put down your 38 spots, you can make buckets for this is 1, this would be 2, 3, 4, 5, 6. It goes into one of these all the way up to 38. Okay? Now, the wheel, it's a wheel, and it's very well manufactured. So what do you think the distribution, if you made a histogram, you sat there for 5 days, and every time you got 2, you put a brick on 2. If you got 5, you put a brick on 2. What do you think the distribution would look like after 5 days of observation?
A brick wall.
No, careful now. Careful. I mean, you're right, but come on now. You guys, you're missing the crux. This is a true story, okay? I'm not making this up. This is not one of some stupid... I'm not joking with you guys.
Well, it would be lit like a straight, just, it would be like a straight line, right?
Okay.
If the game is completely fair.
It is fair.
Okay.
It was fair then. It was fair. Now you've got to put yourself in the mind of this student. What do you think? He's a physics major, right? What do you think is going through his mind when he thinks about roulette? He's going to beat the game. In 1959, I was 3 years old. He's going to beat the game. How? Why would he even think that? I mean, this is a terrible game to play, you guys. There's a loss. We already computed, or we'll compute the expected loss. It's not good on roulette. So he made a histogram. What do you think was revealed by that histogram?
Imperfections?
It was not. Okay, so it was not this, but it was little deviations from flat. It was not flat. We call uniform in our class, but there were variations. Now, why the hell? Now, this is after watching for 5 days. And of course, he can't. How to plan himself there? It would draw suspicion. So he had some buddies to help him do this. They did shifts and they recorded. So what do you think? What do you think? Why would there be? And we're talking about a lot of data here. So these are not just an artifact of a small sample size. These were real. Why is that possible? How could that be possible? Roulette wheels are manufactured if you've ever seen one, it's a work of beauty. It's made out of wood, but it's beautiful. Why would there be imperfections?
Maybe the paint.
It was the wood. Always in a rush to manufacture something, right? What kills you when you're making furniture or something? What's the one thing that can kill it? if you're doing the Vermont Northwoods, woodworking craft, what's the one thing you have to avoid? Is this story too long, Aim? I'm sorry. Am I putting you to sleep?
No, you're fine. I'm just not entirely I'm not too sure on the physics of why something like this would happen.
It happened because those are manufactured out of wood.
The hardness of the wood?
No. When you manufacture out of wood, there's always this thing about, well, how long do we let the wood cure, dry out? And wood starts out green, hardwood. No, it's just hardwood. It needs to be dried out for months. Otherwise, it starts to warp. And, it's just this effect of life that there is shrinkage, that goes on when it dries out. And the result of the histogram is this. So what then? How did he exploit this to get money to buy a yacht? What would he do?
Well, he'd bet on the higher bumps.
Yeah, this probability now is not 1 over what? Theoretically, the probability of getting whatever number that is, say 37, is what? 1 over 38, right? But if it's not, if it's different than that, you can exploit that. I mean, yeah, on a higher bump, right? Because it's more likely. He had a bit of a bankroll, but they stayed there for like weeks, a few weeks, and they got their $300,000. You might say, come on, 1957, $300,000. Did you need that much? Yeah, those stupid boats are really expensive. They're not cheap. They're still expensive. They're more expensive than houses. Okay, that's the story. That's a histogram. That's the use of a histogram in a practical situation. You can discover a story in the data that you might not have seen if you just had a long list of numbers, okay? You know what I mean? The numbers would be 37, 5, 7, keep up 1, green, double green, like that. This is the thing about histograms. This is the first thing you do with your data. You want to try to discover what it's telling you. Okay, so every story has an ending. So there was an obituary for this guy a few years ago, and what do you think did him in? I'm sorry, what do you think did him in? Oh, I'm losing somebody. Am I already at the end?
Yeah, basically.
So what activity did this guy? Do you remember that was it in Arizona or something? There was this biosphere project or something like that, a totally self-contained. It was a building that was totally self-contained, and there were plants and stuff in there, and they were growing things. And there was it was sort of like what you would have if you made a community in a station on Mars. It was completely cut off from the outside environment. Does anybody remember that? What that was called?
I've heard of it. I don't remember what it's called.
Well, he was part of that, and he blamed his days there or his year. I think they did a year. He blamed that. He said weakened his body, and then he had medical issues, health issues ever since from that. He said that the air didn't smell very good. Also, on top of it, I don't know if that'll kill you, but okay. I'm sorry I didn't cover as much as I wanted to do. But there's a week, right? And could you do me this favor? Could you read through chapter 4, and not the hard stuff at the end of it, but the beginning to the middle of it? And as I said last time, the author has taken a lot of time to do problems that are really too simple for you guys. But I think, look, some people are learning this the first exposure they had. So why not do those simpler problems and work them out? And those are the examples in the book, okay? And in the meantime, I'll be building the test and get it to you, and you'll be able to look and say, well, where does this show up in chapter 4? What does this have to do with it? So I'll this is the plan. So, but you have to spend the time to understand the basics of chapter 4, okay? Just the basics. And you'd be surprised. We can do calculations, but then we don't know what we're doing, But try to understand, his examples. He has some examples where he's comparing probability to expected value, and they're sort of subtle. I would settle in on that. There's something about buses, and I forget what problem that is. It's example 3D. 3D. So that would be a good example to sit down, get comfortable, spend about 40 minutes with that, okay, until you really understand what's going on. Again, I'm sorry about my stories, but I don't know how else to teach histogram without that story is like the number one story for histograms. Okay.
And it demonstrates what it is, which is helpful.
But it shows you that there could be a story lurking in your data that you don't observe otherwise. Our eyes are good at seeing patterns. Okay, I'm sorry if that was too bored the hell out of you, but I felt like I needed to and honor that guy, to tell you. Okay, so one last question. I see how smart you guys are. How do the casinos protect themselves from this type of attack, or if you want to say it, is this type of technique? How do they? So now that we know that the tables are not, the roulette wheels are not completely perfectly manufactured, how does the casino then? Because you go into a casino, you'll see roulette wheels. So how do they fix the problem?
They detect the strategy basically. I believe they find anyone who keeps betting on the same thing probably and kick them out.
Well, he had about a 3% advantage, is what I read. You don't need to bet. You don't need to bet that long on 3% if you have a pretty good, if you have a bankroll. So, okay, how do they do it, you guys? This is my parting shot.
That's a lot more than I expected.
Yep, you can read about it. AIM, how do they do it? How does the casino? What do they kill these people they see doing? How do they do?
I think they do.
I told you this story where I met somebody an underworld person who was whatever. I met somebody who was beating people up. Okay, but that was from the 70s or something. But anyhow, so how do they do it? Come on, you guys. It's the last question.
No.
They probably swap out roulette.
Yes, Ethan, you scored another hit. Okay, so now you're just
Yes.
rolling and go. They just swap them out when people are not looking, and they all look the same. And they just swap them out, so you don't know which one you're. They have like about 10 or 12 in the back room. And they just in the wee hours of the morning they'll swap it out. It's just simple. It's just. But they do it. This is one of the weaknesses.
Just have to analyze every single one now, and then calculate the probability between all of them.
You don't know. They all look the
cost
same.
average it.
They look identical. I mean, and they don't let you mark them. They look identical. All right, you guys. I'm sorry about this. Me and my stories, but I would be.
That was pretty interesting.
Somebody says invisible ink.
Mm-hmm.
So anyhow, the guy that I met, he's a friend of a friend. He wouldn't look anybody in.
I like that.
I already say this story to you guys. He wouldn't look anybody in the eyes, and I'm saying, what's wrong with him? He doesn't communicate with you. He doesn't look at you when he talks to you. And my friend said, well, he's killed 3 people. It was all business. He spent a majority of his life in prison. And apparently, if you've been in prison, you don't look at anybody. That's looking at somebody is like a prelude to fighting somebody. So
right, fair, but like I also work with students with autism, and they also don't like to look people in the eye. So I try not to put too much weight on things like that. Like, well, sometimes there are people who are just neurodivergent, and that's just how they are. It's okay.
Autism is a spectrum, right? It's a spectrum. So
you can meet one person with autism, and well, you've met one of them. It's very different and different symptoms for every different person.
My son had on the spectrum, and I noticed in preschool he wasn't participating, and they were doing their ABCs, and he couldn't. He looked frustrated and stuff, and we got him out of there real soon. Got him to a psychologist, and they did a IEP, and it was a spectacular turnaround.
Mm-hmm.
He was not talking. And you know how they do that song for the ABCs, the alphabet song?
Mm-hmm.
So I got his sister to sing it to him, so he can learn it. And she goes,
yeah, you do have to approach differently, but, it is definitely like, it's not like I look at a student with autism and I immediately know how to teach them, because, again, symptoms are different for every different person. But I will say, though, that like working with students with autism versus ADHD, I can do pretty much the same thing. Like those two are so related that it's a pretty like similar strategy. But everything is just taking your time, figuring out what works for them, what doesn't, and definitely trying not to take things personally if they act differently. So like if they don't look you in the eyes, it doesn't mean that they're not listening. Mm-hmm. Or if they don't talk to respond to you, you learn how to give them like hand signals to say, okay, are you good? Do you want me to do it again? Something like that, so they can talk to you without talking. Like you learn strategies, things that work for them.
My daughter, this is how she got through. Do you know the song for the letters? A B C D
ABC song?
H I J K L M N O P Q R S T U V W X Y and Z. Now you know your ABCs. Just don't bother me anymore, please. And he laughed, and there you go.
You liked it. Yeah.
They both started singing it that way, and they said, "Crazy." He said, "Oh, I sang it to my teacher."
Oh no!
So I said, Nikki, was she smiling? And he said, "No, she was upset."
Oh man, but if it gets into a point where he can use it, then you've succeeded as a teacher. So
But I'll tell you, it's a struggle to this day. He got a 790 on the math SAT, and he didn't study.
That's fantastic.
He didn't study for it because he felt it was beneath him to do it, because he felt like you should know this stuff. But I don't know. He just can't. There's something about ambition. He said SMC and getting B's. Mm-hmm. I hope, it's like you can't.
Well, I mean, also keep in mind that like transitioning from being in high school to being an adult, sometimes you're going to have to just let them learn the hard way. Don't kick them out of the house or anything.
Yeah, right.
But sometimes life experience is the best teacher, unfortunately.
It's kind of hard to get any experiences now because everybody's cooped up. I mean, he's still
Yeah,
he loves
it's
to
true.
be out with his friends, but he's nice because he could get infected and bring it back to me.
Yeah,
I'm old, and I'm afraid that might be the end of it. Might be the end of it.
that would be bad.
You'd have to get a substitute teacher, and they would say, "I'm going to teach like this time."
Mhm.
It's writing so fast you just barely have time to write it down on your paper, and now it's turn the page. I've had teachers like that, and I say to myself, nobody learns that fast. I mean, what are you talking to, Superman? All right. Oh my gosh.
Okay.
10 people here, and I've got no
Well-
text to give you.
got no
Well,
way?
it happens.
What happens? Shit.
If you don't have a test to give us, is that what you said?
No.
I might
Yeah,
have misheard
I
you.
feel bad. I know what to write down, but I got caught up in committee work yesterday that prevented me from.
I have another professor who does take-home tests, which I'm so glad about. And yeah, he was going to give it to us yesterday. Didn't have it ready, but his resolution was he'll email it to us.
Does he allow use of Chegg or Slater or those other places?
I mean, yes and no, in the sense of like you can use online resources, but don't ask someone else to do it for you. And his thing was the dean is looking into it. The dean wants to check, kind of like put a stop to that sort of thing and count that as cheating. So if you can prove that a student specifically looked it up, to punish them for it. So
There was a famous story that a professor or a TA put a wrong answer in Chegg, belonged to Chegg and put the wrong answer. And then everybody in his class gave that wrong answer on the test. And apparently
that's
pretty cruel.
but it had some sort of legal implications. So the person that got in trouble was the TA. I think he got fired.
yeah,
There's some sort of thing where you can't, what do you call it, entrapment? You can't.
right. Yeah.
That's a serious protection you have.
That's interesting.
I don't know. I just happened to notice in our class that everything got checked, but it was at the last minute, which is really weird. Maybe people just checking whether they have the answer right. And I know you guys. You would tell me if you're checking. I know you. So it must have been one guy who was working solo or that just checked.
Mm-hmm.
He just decided, look, if I'm going to sin, I might as well go to the max. I'll get forgiven later on. So why don't we just go for it,
That's funny.
Well, I guess I'll see you after spring break.
Yeah, be safe. I don't know if you're traveling or are you traveling anywhere?
No, I'm having to do my what's it called? I still have classes over spring break because I'm doing 391, the field experience.
Yes.
And the high school I'm teaching, I'm doing my internship at, has their spring break later. So I'm still kind of like not exactly getting a break. Oh well. No
And
big deal.
the week goes by pretty quick, unfortunately.
Yeah, that too. And then it's over.
What did Janet Jackson say? Time flies. What was that? When you're having fun or something? Time. Whatever. There's a famous song, and she.
Mm-hmm. Okay. Well, regardless, I still have another class to go to. So take care.
Okay, and thanks for attending. Thank
I'm
you.
gonna go. Bye.
Bye, Ethan. Nice seeing you.